Hello, geometry. Here we go with lesson 4. Pretty easy lesson, but at the same time, the explanation part can kind of trick people a little bit, but pretty common sense for the most part. So here we go. We're going to introduce chords. So a chord, looks like chord, but it's chord, is a segment whose endpoints are on a circle. A chord that passes through the center of a circle, you know this one is called a diameter. So all diameters are chords, but a chord is not necessarily a diameter. Okay, so in this circle pictured here, a diameter is represented by AB. Should know that one by now. A radius is represented by OC or OB or OA, but you should know that one by now. A chord that's not a diameter, I'm going to point this out. A chord is, AB is a chord, but a chord is also PQ. Right. Now, there's a lot of theorems associated with these chords. Okay. And this is what I'm talking about. Most of them make sense, like common sense. It's like a duh. All right. So within a circle or in congruent circles, congruent central angles. So I have two central angles that are equal. They have congruent chords. Okay. So let me just show you real quick again and really point this out earlier. So if I have a central angle, right, the chord that connects those endpoints, okay, is what I'm talking about there. So if I have, back that up a little bit. If I have, we know that this angle and this angle are congruent, right? I can conclude that those chords are congruent. That's what that's saying. Okay. Let me go ahead and get rid of that. Okay. The theorem continues. Congruent chords. So if I have congruent chords, then I have congruent arcs. And then if I have congruent arcs, then I have congruent central angles. And we knew that one already. All right, so they kind of, if one thing's congruent, then they kind of all are, is what this is saying. In the diagram below, circle O and circle P are congruent. That's given. That is important because if they're not congruent, this theorem doesn't apply. I'm telling you that arc BC is equal to arc DF. If that's true, what can I conclude? Well, if the arcs are congruent, then the central angles are congruent. So angle BOC is congruent to angle DPF. The other conclusion then would be that the chords created by those central angles, so BC and DF, are congruent. Okay, that's all that's saying. Basically the same thing here. So the previous example had two circles that were congruent. This next example, it's one circle with multiple chords, multiple arcs in it. So what information is given? All right, so I'm looking at this. What do I know? I know that arc QS is congruent to arc RT. If the arcs are congruent, then the central angles are congruent. So RPT is congruent to angle QPS. And then the arc, the angles create congruent arcs. So QS is congruent to RT. Okay. To the back for more theorems. Within a circle or congruent circles, again, it's got to be within, or it's got to have congruent circles here again. Chords equidistant from the center are congruent. So if they're the same distance to the center, then the two chords are congruent. The converse of that is that congruent chords, if I know the chords are congruent, then I know that congruent chords are equidistant from the center. Yeah, so if I have congruent chords, I know the chords are the same length, then I know that they're the same distance from the center. So I'm going to show you both of those situations here. So the first one, find the value of A. So A is, I want the length of that chord, put an S here. I want the length of RS. Well, what's given to me? I see the 9 and the 9. Now, that's the distance from the center to the chord. And I know that because of the right angles. Without those right angles, I don't know the distance. I talked about that in the first semester, but those right angles are important. So the distance from the center to the chord is equal. Because of that, I know the chords are equal. Well, PR would be 12.5 plus 12.5, right? Because those are equal. So it's 25. So A would be 25. So the explanation would be, I was given chords equidistant. So I'm going to say equidistant is congruent distance to the center. I could conclude that the chords were congruent length. Okay. Next one, find the value of X and explain. You could probably look at this, it's probably 16. And you're right, X is 16. The explanation is the hard part. Well, what did I give you? I gave you congruent chords, right? 36, and this one's 18 plus 18, so 36. So I gave you that those two chords have the same distance or same length. What I can conclude is they are equidistant to the center. Equal, spelled equal wrong, sorry. Equal distance to the center. All right. So, there's more theorems, of course. In a circle, okay, a diameter that is perpendicular to a chord bisects the chord, cuts it in half, and its arcs. This is not technically the converse. I don't like the word converse here. It kind of switches these two things. It's not technically a converse, though. In a circle, a diameter that bisects, so if I know that it bisects the chord, then it is perpendicular to the chord. So in the first one, theorem 3, I know that it's perpendicular, and I conclude that it's bisecting. In the second one, or number 4, I know that it's bisected, therefore I know it's perpendicular. Okay, and the theorem 5 kind of puts it all together. In a circle, the perpendicular bisector so the one that cuts it in half and hits it at a right angle contains the center. All right, so they're all basically saying the same thing, just a little differently with what you're given. So let's do the last 3 examples. So there's no diameter there, right? There's a chord, LM is a chord. It doesn't go to the center, so it's not a diameter. But there's that dotted line there, which hits the center. If I would extend that, I would make a diameter, right? So when I say in the theorem that it's a diameter that's perpendicular to the chord, I mean a line that contains the center. All right, so what we have here is a line that contains the center that is perpendicular to LM. Since it's perpendicular, I know that it cuts it in half. That's what theorem 3 says. So this is 7, and this is 7. And that was my explanation here, is basically what I'm doing. So diameter is perpendicular. Therefore, okay, it bisects the chord. That's the theorem I'm using to help me answer this question. I haven't answered the question yet. But now what I have here is a right triangle with the 2 legs. So I can do 3 squared plus 7 squared equals r squared. So I get 9 plus 49, so 58 equals r squared. Take the square root, and you should get 7.6. Let's check it real quick. Yep, 7.6. Okay, switch colors. All right, so what's this one showing? I don't have a right angle here, so I can't do the Pythagorean theorem yet. But what I have here is that I have a line that contains the center, so BC contains the center, but that line bisects. I know it bisects because the two sides are equal. So what does that mean? Well, if it bisects, that means that that line is perpendicular to the chord. Now I have a right angle. Now I can do the Pythagorean theorem. So 11 squared plus y squared equals 15 squared. And I get y squared equals 104. Square root of that. And you should get 10.2. So I was given a chord that was bisected by a diameter. So chord bisected by diameter. I conclude that the chord and diameter are perpendicular. Right. Last one, sort of, we want to find the length of the chord here. I told you that that's perpendicular, right? So it's a diameter that's perpendicular. So I'm given a diameter that is perpendicular. I can conclude that the chord is bisected. It's the third one, I guess. Not the third one, but like the number 3. So I know that these two things are equal. Well, if I can find this one, just double it and I get the whole thing. So that's Pythagorean theorem again, 4 squared plus x squared, not x, sorry, I'm not going to use x. I'll call this one y equals 6.8 squared. And you should get y squared equals, let's see, 46.2, no, 6.8 squared minus 16 is 30.24. And take the square root of that. And you get 5.5 roughly. But that's y, so I need to double that. And I get 10.99 or 11.0. Okay. Last one, just using this a little bit more. Find the distance from the midpoint of the chord to the midpoint of its minor arc. So in number 3, so I'm looking at the midpoint of the arc, which is right there in the middle. I'll change to a different color here so you can see it better. Midpoint of the arc, or sorry, midpoint of the chord to the midpoint of the arc. I want that distance. Basically, how much further do I have to go to get to the circle? Well, it's 4 from the center to the first point, and I know that the radius is 6.8. So I know the whole thing has to be 6.8. Just making sure you're using everything you know here. Should get 2.8. Okay, doesn't really relate to chords here at all. It was just a problem-solving question that I saw and thought I would ask. So that's it for chords and arcs. We got inscribed angles coming up next.